So let's take a look at an example of what a limit of such a function might be. So let's say that our set is, our domain are all the 1 over n's, where n is natural, so that's 1, 1/2, 1/3, 1/4, etc. And the outputs of my f of x are just going to be x plus 2. I am going to wonder what the limit of f is as x approaches the only cluster point of S, 0, is, and our intuition probably tells us 2, right? The x's get closer and closer to 0, f bumps all those up by 2. I really want to believe that that is 2. But as before, if we want to show this, then this requires some sort of proof. So let's go ahead and take a shot at this then. So we let epsilon be greater than 0, and so that is once again some sort of ball around the alleged output or the alleged limit of L being 2, right? And I want to know how close do I have to get to be on the bottom to be within 2 of that output. So note that at least down here, right, this is a linear scale. So if I put epsilon down here, epsilon plus 2 is definitely epsilon away from 2, right? So what I'm going to do is I'm going to let delta be epsilon over 2. That's going to be my delta. It's just going to be smaller and coming in closer here. So if delta is epsilon over 2, then for all x in 0 minus epsilon over 2, 0 plus epsilon over 2, delete 0, but that's not in my S anyway, right? Well, the difference between x and 0, that's less than epsilon over 2, right? So the difference between f of x and 2, which is allegedly my L, well, f of x is x plus 2 minus 2, which is less than epsilon over 2, which is less than epsilon. So that shows that as I get closer and closer to 0, my outputs get closer and closer to 2. There really isn't too much to show in a concrete example like this. I thought it would be helpful to take a look at maybe some explicit examples. So we've dealt with some weird domains, but let's just go back to our favorite domain of all, R itself. If we can get away with it, we should. So let's take a look at R and look at some examples here. Now, let's pick a C. Let's pick a C of 1. Let's say C is 1. My f here, as you can see, is x squared. You know what? Let's do something a little bit different. Let's pick a C of 2. All right. So as x approaches 2, what should my outputs approach? Well, our intuition probably tells us 4, maybe, right? So but L will be 4, And look over here, I have my epsilon is 1 and my delta set to 1 as default. So if I drag over here, here's my epsilon of 1. My deltas of 1, they don't quite do the job, right? Delta of 1 is a little bit too big because I'm going down to 1 here, and way up here, right? Those are my outputs. So a lot of these inputs are falling outside of this epsilon ball. I need to shrink down this delta by quite a lot. But if I look at this and I say, hey, now that I shrunk my delta down, everything that's inside this delta radius, all these outputs do in fact fall within my epsilon radius. If I shrink my epsilon radius some, that's okay. I can shrink my delta radius down even further. If I shrink my epsilon radius down some more, I can shrink my delta radius further, right? Now here is what may seem like a silly question. Could the limit also be 3? Well, that doesn't seem like it's very reasonable or possible, right? But let's go ahead and ask that question about 3. Well, here I have my epsilon radius of 1, and my delta of 1 doesn't work again. So, all right, let me just go ahead and start shrinking. Well, it doesn't look like I can shrink it enough, right? No matter how far I shrink it, I still have stuff landing outside of this epsilon ball. And of course I do, right? No matter how close I shrink towards 4, and in fact, let me do one better. Let me shrink epsilon down just by a little bit, right? That really highlights it. Then no matter how far down I shrink my delta, there's going to be stuff down here that shoots up outside of my epsilon radius, right? And it's impossible for there not to be, because my outputs are getting closer and closer to 4. At some point, that's nowhere near 3, right? So there's no way that I can get small around 3 and say, all right, now get close to me if I'm getting close to 4 instead. That's just not going to be an option. So we can see that that for something like this, 3 can't be the limit as x approaches 2. Only 4 could be the limit. What about a function like, let's say if x is less than 1, then you're 0. If x is greater than 1, greater or equal to 1, then you are x. And let's C be 1. Let's let epsilon and bit delta go back to being 1. And let's ask, all right, is there any reasonable thing we could call a limit? Well, maybe 1 could be the limit, right? That seems like a reasonable output. Let's let L be 1. All right, let's shrink down epsilon a little bit. Let's say epsilon is 0.25. That's pretty small. So let's start shrinking delta. But I shrink delta down. All right, at some point, my outputs here, they're okay on the right side here, right? Those are fine. But my left-hand outputs are still always going to be down here at 0, right? Anything less than 1, its output is always 0. It's not going to be anywhere close to 1 if I make my epsilon small enough. So, no, it doesn't look like 1 being the limit of this function is going to work. Alright, well, since I'm stuck at 0 here, could 0 be the limit? And again, we see like, no, it cannot. If we're stuck here at around 0, then these values over here, those work out fine, sure. But for anything greater than 1, no matter how small my delta is, I'm always going to pick up something up here, right? In this region up here, all my x's greater than my 1 are going to shoot up here close to 1, away from my 0. So there's no way that 0 could be the limit either. And it's pretty clear that nothing in between could be the limit. I make my epsilon small enough, now there's nothing there, right? And so in a case like this, we would say that the limit's not defined, right? There is an epsilon so that no matter what delta is, right, 0.00001, whatever delta is, no matter what L I try to choose, there is no limit there. Okay. For the last, or sorry, not for the last, for the next video, we've been talking about different notions of closeness. We're talking about functions' behaviors as they get close to something and not close to something. So for the very last video, at least that I'm going to record today, we're going to tie together the limits of a function and sequences. All right, thank you.